So hi everyone, good morning. My name is Ran. This is a joint work with my advisor Ronen Brafman, and I'll tell you this morning about a compilation-based approach to conformant probabilistic planning with stochastic actions. So the outline of my talk, I will start with introducing the problem and some basic notions. Then I will review the previous approaches and the challenges this problem has, and then I will describe our contribution, the algorithm, and we'll conclude with some results and future work. So to make a long story short, the problem that we're trying to solve is a simpler model than the ones that we talked about in earlier talks. And this is the problem of conformant probabilistic planning, or CPP in short. And in this problem, we're trying to find a plan, not a conditional plan. We don't have observations. We want to find a sequence of operators, and we want to map the initial state to the goal. But the initial state is given to us as a probability distribution over word states, and stochastic actions are in place. Another important part here is that we need to achieve the goal with some high probability that is given to us as a parameter. So this is a small example of a CPP problem. And here the skewed monster can be initially located in each of those four possible locations with those probability. And let's say we have another kind of uncertainty, another layer of uncertainty in the initial state about the possibility that the cell C2 is locked with a probability of 0.08. And we need to bring the monster to the goal. Actions are stochastic here, so any move has a success probability of 0.95. But if the destination cell is locked or does not exist, then nothing happens. And let's say that we need to achieve the goal with probability of at least 0.6. So the key observation in our solution is that a deterministic conformant probabilistic planning problem can be solved if we will identify a subset of the possible initial states with probability higher than 0, that has enough probabilistic mass, and there's a conformant plan from those states. Then we can get a plan for the original conformant probabilistic planning problem. So our solution combines a few techniques and includes 3 stages. In the first stage, we identify a promising set of those initial states. This is the restriction stage, and we do it using relevance analysis. To get rid of the stochastic operators, we use determinization. And we get a deterministic conformant planning problem that can be solved by an off-the-shelf conformant planning solver. So the key contributions of our work is a new CPP solver called RBP+, which extends our previous CPP solver, RBPP, to partially support stochastic actions. So basically what this solver does is restrict the initial state and determinize, and by that compiling the probabilistic problem into a non-deterministic problem, and with deterministic actions. This method is novel in the sense that it combines the ability to handle both kinds of uncertainties, the initial distribution and the uncertainty about the action's outcomes, and it does that using compilation approach. And by doing that, we avoid the shortcomings of using classical planners directly. And maybe most important is that our algorithm is more scalable and efficient compared to previous solvers. So more formally, a CPP task has its finite set of variables, of course, set of operators that some of them might be stochastic and commonly include conditional effects. We have an initial belief state given to us as a probability distribution, a goal description, and we need to achieve the goal with probability higher or equal to theta 0.6 in our case. So this is the representation of the initial belief state, basically clauses that describes the uncertainty, and unit clauses that describe the certain parts, that all the other cells are not locked. This is an example for a specific conditional effect of a specific action. So if we're at B2 and A2 is not locked, then in probability of 0.95 we'll get there and in probability of 0.05 will stay in place. The basic motivation for this not so natural setting of conformant probabilistic planning for our research is that this is a very simple form of probabilistic planning, and it allows us to test and try the compilation approach with the hope to extend it in the future to a more sophisticated and more complex probabilistic planning models. So a word on previous approaches. One of the most common approaches was to heuristically, for conformant planning and conformant probabilistic planning, was to heuristically search the belief space. Significant work in this area is PFF by Hoffman and Domschlag from 2006. The approach, although successful in some benchmarks, suffers from two obvious disadvantages, which are that the belief space is huge and it's hard to represent it implicitly, even implicitly, and that attempts to find good heuristic for this space or generalize classical heuristics were not so successful. The compilation approach that we take has its pros and cons also. So the main pros are that it's so tremendous work in the last couple of years, and now we have very good compact representation of the belief space as a belief space of a simpler model or as a classical space. And of course, the basic motivation here is that non-probabilistic planners and of course classical planners works well, works fast, and are much better and faster than existing probabilistic solvers. The cons are that classical planners were not meant to solve those compiled problems, which typically includes numbers and cost bounds and conditional effects. And now compiled problems are usually pretty big, and classical planners are not too successful in solving them. And that, once again, classical heuristics are not suitable for the task that we're asking them to do, finding a good set of initial states in our case. And when we enter determinization into the picture, it's even, it has its own drawbacks, of course. So back to our example, we'll describe our algorithm. And in a very rough overview, our algorithm has a few layers of compilation. And the first layer is the restriction process, the process where we select a subset of the initial states. This takes us from the original conformant probabilistic planning problem into a conformant planning with stochastic actions. We call it a stochastic conformant planning problem. It's a very weird creature, but we immediately get rid of it, and we, using determinization, we get a deterministic conformant planning solver. And a more technical step is that we solve this conformant planning problem with a cost-bounded classical planner, so we further compile it afterwards. And at the end, we get a plan that is easily translated back to the origin, to be a plan for the original problem. Okay, so one of the first decisions that we need to make is we have this probabilistic gap, we call it. Okay, so I have a legitimate 0.4 probabilistic mass that I can take the risk not to succeed in, and I need to decide how to divide it. What will be devoted to the initial uncertainty and what will be devoted to handle the stochastic effects. What we do is that we take care of those two kinds of uncertainties independently. It means that we decide on some of this mass to be devoted to the initial state restriction, and the leftover is used as a plan risk allowance. I will not elaborate about the decision, but the main consideration here is to have as much as possible restriction weight, so we can significantly reduce the initial state uncertainty, because we found that this is the main bottleneck in the ability of the underlying solvers to succeed in solving the compiled problems. So the first stage is the restriction. We go from, move from some probability distribution into a non-deterministic, a set of possible initial state that we select in this process. In our example, the planner chose us to ignore the uncertainty about C2 being locked, so we assume it is open, and we ignore the 2 of the 4 possible locations of the cute monster in the initial state. Okay, so we got a new initial state described like that, and the probability of the initial states that we are left with is 0.71, what means that we have another 0.84 probability mass to take to the plane risk allowance. So the restriction process is actually part of our previous planar RBBP, and I refer you to the paper for details, but I will just say that this restriction is done using some heuristic parameters that it determine which of the uncertainty is better to restrict, and using those heuristic parameters we determine the order of restriction and the initial states we choose to ignore. This process is iterative, and of course it terminates when no further restriction is allowed, given the amount of probability weight that we decided on. The second stage, so now we have a stochastic CP, as I said, and the second stage is to determinize it further to get at a deterministic conformant plane solver. Okay, so we use a version of the all outcome determinization. It means that we create a separate action for each possible outcome. And to reflect the original probabilities of each outcome, we model the probabilities as action costs, and we move to log space to allow modeling products as sums, because we're going to use a cost-bounded planner that doesn't know how to work with products. A few more words on the determinization process. We assume here that conditional effects of the same action are mutually exclusive, and this allows us to determinize each conditional effect separately. It allows us to capture at least one successful execution. As much as it doesn't look like that, it may capture more than one execution, and we'll soon show you how. And but of course, it is an incomplete scheme. But surprisingly, at least for us, it was pretty successful, at least on the existing benchmarks. Another important component of our algorithm is the repeatable actions mechanism. A repeatable action is basically an action that you can repeat in sequence a number of times, so that each new execution of the action increases the probability of the outcome to succeed. I must say that repeatable effects are very common in probabilistic benchmarks and in natural settings. Repeating it increases, of course, the plan's success probability, and in many cases, one must figure that he needs to repeat this action in an early stage in order for the plan to succeed. And one of the reasons for the failure or unscalability of previous planners was that they failed to figure it out in an early stage of the plan. What we do is to identify those repeatable actions as part of our determinization process, then create some finite set of copies of each of those actions. For example, if I'm determinizing A epsilon I, so it represents I sequential executions, and we can attach it to the suitable probability of it after those I executions. And of course, we translate it back to the original sequence when returning the plan. Going back to our example, so we are now left with a simple conformant planning problem. We have two possible initial locations. We need to bring the monster to the goal. And the plan, the output plan, the plan that we return is this plan, going to twice up, 3 times right, 2 times down. And it is based on a conformant plan, which means that we repeat up twice, then we do a signal right, then we use a repeatable action of 2 rights and going twice down. For example, the probability that we'll be at A1 after 2 execution of ups is 0.9975, much more than a single execution. And we succeeded to solve the whole problem because we figured that it will work in the in an early stage of the plan. Okay, so in general, you can see the other probabilities of executing this plan. And what we get is a plan with a success probability higher than 0.85, and combining it with the deterministic, combining it with the initial state restriction earlier, we get a general success probability of I or equal to 0.6. A few words about the algorithm properties. So the algorithm is sound, but like any compilation-based algorithm, its soundness depends on the soundness of the underlying solver. But of course, as I said, it is incomplete, and both sources of incompleteness come from the fact that we avoid iterating over exponentially many possible restrictions of the initial state, and we use a pessimistic evaluation using determinization, and we may not capture a successful execution. Concluding with some results, so this is a part of the experiments that we've done comparing to PFF. We evaluated our planner both on parameter of time and plan length. And you can see that on simple problems as like slippery gripper with one block or sandcastle, PFF tends to be a little better. This is because we have a big overhead because of all this compilation and relevance analysis. And but as problems get more complex and more complex in a few directions, more complex initial uncertainty, higher value of theta. Okay, as higher as the theta value is, as higher is to plan for it. We see that PFF fails to scale up and handle it, while we have in most cases reasonable plan lengths and times. The main points, as much as I see it in the results, is a good point to know is that we integrated this repeatable action mechanism actually into the PPDDLs that we used as an input to PFF. And it did improve the running times, but had no effect on its scalability. And it demonstrates mainly that while in principle we ignore some valid solution plans and we use a very pessimistic evaluation, then we are still able to solve very good most existing CPP benchmarks. So it can tell you something about those benchmarks or the nature of CPP problems in general. For future works, I would like to add the ability to find not only a repeatable action, but repeatable sequences of actions. This is also very common, and we cannot handle it right now. And to improve the determinization so it can focus on relevant outcomes only, so we can obtain more accurate estimates of the success probability. That's it. Thank you.